there are elements of linear kinetics that we want to feature here in this video. We want to talk about friction and pressure and how best to push and pull. So in terms of the appropriate amount of friction, this man was warned, or this guy was warned, that it's icy, the coefficient of friction is dropped, and he's suffering the consequences of having not enough friction in order for him to get on up the hill. And the symbol that represents the coefficient of friction is mu, and it's the product of the force necessary to slide an object divided by the force holding the object in place, and the closer mu is to 0, the less friction there is. So what I really want you to take away from this is that as a student of movement, be it athletic movement or in daily life, you've got to be a student of how to have the ideal amount of friction. You wouldn't think about, as an intramural basketball player, or you wouldn't expect if you went to one of our women's basketball games to see people wearing socks because the coefficient of friction is inappropriate. Likewise, you wouldn't expect in a speed skating contest that people would wear work boots. The idea is that you have to make specific the interface with the supporting surface with the appropriate amount of shoe wear, and that's why it's kind of interesting that a decathlete will have a whole, or a heptathlete will have a whole bag full of shoes, because the necessity for friction is different in each of their events. Factors influencing the value of mu, or the coefficient of friction, are the relative roughness and hardness of the surfaces and the molecular interaction. So be a student of what the appropriate coefficient of friction should be. And then push or pull. Push or pull. My point here is it's difficult for this alligator hunter to push the alligator up out of the water. Not so safe. These people are doing seismic measures out in farmland, and when this seismograph sends a certain kind of a message, then they're doing markings in the field. And so it could be geological studies for excavation, or for archaeological digs, or whatever it might be. Let our imagination go. This would be a tougher task if this man who was providing the force was pushing this through the field. The reason is, as he pulls this, it lifts the front edge of their seismograph. There's actually a vector force where this is moving up away from the supporting surface. If we were to pull this, the vector force would be pushing it down into the ground. So make a choice. There are times when pushing is really your only option, but pulling an object, the front edge gets lifted off and it's more efficient. So here are interpreted principles for pushing and pulling. The internal force must overcome inertia and friction. You can wrap your mind around that. This seismograph, when they set it out of the truck, had a quantity of inertia. It's not going to move on its own. It's not motorized. It has to have force applied to it. In this particular case, they've made the choice to pull it. For maximum force, use the maximum summation of internal forces. That means that if the human body is going to propel this, we need to use the various body segments to maximize the amount of force to move. And internal force really means that it's muscular contractions. For maximum accuracy, If you have to pull something into a very narrow space or push something into a narrow space, then probably you're going to use finer movements to control that when accuracy is required. For change in momentum, it's way important that that the force needs to be applied over time, and that would be impulse. And I'm going to talk with you about impulse here in just a second in the context of staying safe. How do we prevent too much force applied to a very specific region of the body? If the force is too great and too focal, then tissues can be injured. And then obviously it's way important to apply any force in the line of the object's center of gravity if you want linear displacement without rotation. We don't want rotation. We want linear displacement. It's best to apply the force through its center of mass. I think about that. Here you go. If I took this object and showed you, if I applied a force that was away from the center of gravity, I would get a rotational force. But if I apply the force right at the center of gravity or in line with the center of gravity, I'll get a linear displacement. There are times when it's inappropriate to do linear displacement, and you have to think that through. So that may not seem like a really big bad deal, but it is. Think about where is the center of gravity, and if I want linear displacement, I need to apply my force right in line with that center of gravity. And then I want to talk to you about pressure. This particular player was one of the great all-time defensive players. He would never just dive for a ball and fall into the turf. He would spread the force over area. We want to reduce the pressure. If the pressure is high, if there's focal application of force, bam, like this, we're more likely to have injury than if that force is applied over area. And so he was injury resistant because no matter whether he dove to his left, right, dove for a ball behind him or in front of him, he would end up in this position. He would use a large portion of his body to dissipate the force. So the larger the area, large denominator, the less pressure in any one given area. When the area is big, pressure is reduced and less likely to be injured. Now this PowerPoint presentation, anything that's underlined has a video associated with it. This is in Module 2 under Linear Kinetics. I think you could have fun with seeing in this particular case where there's a basketball referee who goes for a tumble. That's here. And then also the judo fall and roll would be available for you to see. What we need to train our clients, it might be a senior citizen who's been having trouble with falls. We need to practice what happens when we lose our balance. We need to make sure that there's a roll that's associated with it, and so that the area over which the pressure applied is increased, total pressure or the forces applied, then that will reduce the amount of pressure. Pad where you're likely to hit and use, I'll leave that, I'll let that go. And then injury avoidance principles for receiving impact. These are listed for you here, and I don't think I'll elaborate on these. These are available to you in PowerPoint. If we spread out the impulse, large area, maintaining equilibrium so that we don't have a fall, have a large base of support. The impact of the line of gravity should be above the base of support. And then principles for receiving impact. And the very best way to do this is to go get the object and pull it into yourself and dissipate it over time. And then fine focus, obviously, keep the eye on the ball. So these are principles that you might consider. They're for you in print on PowerPoint under linear kinetics, and hope that's helpful to you. Bless you.